This is about the gravitational law. So we're going to look at the one at the bottom here first. There is a gravitational force acting between these two objects, and I just made them in some kind of arbitrary shape, gave them some arbitrary color. There's a mass 1 here, there's a mass 2 here, they have a certain distance in between, and therefore they will experience a gravitational force. Notice that with m1 times m2 or m2 times m1, the gravitational force is the same, and you see that the arrows are the same, just in opposite direction, which also goes with Newton's third law that says there is an equal and opposite force on each of the objects. I'm going to run this here. As you can see, the closer they get, the higher the larger the force is. The acceleration here depends on that force, which is the same for both, divided by the mass of each object. These two masses here are virtually, these two objects have virtually the same mass, so therefore the acceleration is virtually the same, and you probably don't see a difference. And at some point, the acceleration and the force becomes so large that it gets out of the picture. So here we have a small object, here we have a large object, meaning a large mass, and a small mass. Notice that the forces on either one of them are the same, because that's what Newton's gravitational law says, and it's also what Newton's third law says, that there are equal and opposite forces. I'm going to let this run, and as we can see, the smaller mass has a larger acceleration, still has the same force as you notice, but it has a larger acceleration because of Newton's second law, which says we divide by a small mass, so we get a large acceleration. We divide by a large mass, we get a small acceleration on the larger object, and that of course is what we saw. And then they're just going to overlap, bounce off each other. So there is again. So here we have now 3 objects together, and when I let this run, notice that the force, the gravitational force between each of these 2 objects is the same. So this gravitational force is the same as this one, this gravitational force is the same as this one, and this little gravitational force is the same as this one, depending on the masses of the 2 objects. That's why we have the smallest force between these 2, because these are smaller masses, and the largest gravitational force between these 2 objects because they have the largest masses in this trio. Furthermore, the gravitational force, of course, depends on distance. So the closer they get, the longer these arrows get, because now these 2 objects, for example, are closer, so their gravitational force is larger. Notice that the direction also changed, because this one here is at a different angle now from this one. Also notice that with 3 objects, 3 mass, I'm going to reset this here, that with 3 objects, it becomes actually relatively complicated, which is why in astronomy, where we're giving an introduction of what's going on, we like to focus at only 2 objects because it makes it easier. So here we're looking at the planets in the inner solar system, and of course they orbit the Sun. Respectively, they are attracted towards the Sun, and the Sun is attracted to them, and they all attract each other. But as I had mentioned, we like to focus at 2 objects at a time, because it makes it easier, and fortunately the Sun is such a massive object that we can just focus on the Sun and any one of the planets, just one of them at a time, and we come up with a nice orbit for Mercury, or a nice orbit for Earth, or a nice orbit for Mars or Jupiter, and so on, because the gravitational force between any two of the planets, for example Mercury and Venus, is so small compared to the gravitational between the Sun and Venus, respectively the Sun and Mercury, that it can be neglected, and we just look at two objects at a time, mainly the Sun and a planet. Or if we have moons going, where we look at moons orbiting around planets, we just look at one moon around its planet at a time. It just makes it easier. There will be one exception later on when we look at the moons of Janus and Epimetheus as they orbit Saturn, but that'll be in a later chapter. So what we have seen so far is that two masses attract each other. What's interesting for astronomy is that not only do they attract each other like this here, and then they bump into each other, as it's suggested here, but of course objects are orbiting. In order to avoid that they bump into each other, what we would have to have is that one or both objects have some kind of initial velocity. I'm just going to try this here and see what happens. So this object here likes to fly off, but of course it's being pulled towards the left, and that will change its velocity slightly to the left, and then it wants to go up. But then it's being pulled towards the larger object, and so it's going to go to the upper left, and so on, and we're going to get relatively quickly, we're going to get an orbit out of this. There it is. I'll discuss this in a little bit more detail once we get into orbits. We also see nicely here Kepler's second law at work. Notice that the force between the two is the same. We consider that the small mass is orbiting the large mass because it has such a large acceleration, that green arrow that we can see, while the acceleration on the large mass is so small that we can virtually neglect that it's doing something. And by the way, I don't know why it vanished here. The software that I'm using isn't absolutely perfect, and then all of a sudden the other object was gone. Anyway, we see what's going on here.